So yeah, just this presentation just summarize some of the recent developments for the voxel-based different type of solver, like Boltzmann transport, and finite element solver. The main aim is to looking for some collaborators and see if we can develop something application together. So this presentation is I'll present for this work, but this very collaborative work, and acknowledge the contribution from Liang. He's from the industry. He's working as a data scientist in the industry. And Andrew Buchan, he's working as senior lecturer at Cranfield University, London. So we basically work together with several codes. So why we're interested in this voxel-based simulation? Because I don't have the copyright of the images, but this voxel-based simulation have been widely used for the industry or for the games, or we can apply for the AI using convolutional neural network, or using the and there's one very interesting work. I really like this one. Is there's there are group doing shape optimization using the pixel, using the voxel-based simulation to optimize the internal structures of the airplane, and also some other structure. So so basically we're trying to talk about three type of we developed in last 10 years or something. We developed a few different solvers. And I will introduce one by one in this talk. The first one is it's a lattice Boltzmann code. It's open source. It's a very new code. It's developed in this year, and we released it. If you have a look and go into this website, and now currently it's online and received 7 stars so far. So it's quite very interesting. I'll explain this later. It's open source LBM code. And the second one is it's called Raven code. It's a Boltzmann transport solver. It's a direct deterministic Boltzmann transport solver. It's using the Fortran, very old languages with OpenMP parallelization for shared memory, and MPI for. And also the third one is the finite element solver. It's also in-house solver using similar technology, but solving using FEM to solving the Navier-Stokes equation, and including also some of the solid problem as well. So all this mixed together, but they have some similarities. They're all voxel-based. Similar like this. When we do the MPI parameterization, is similar. Like we have a very simple hollow swap between these blocks, and all this code have a Python wrapper, so we can couple all these things together very nicely, because it have exactly the same structure, data structure. It's support a new data structure, so we can do all type of coupling. So now we can solving very micro scale fluid problem using FEM. Also, we can use a meso scale problem using lattice Boltzmann method. Also, we can direct solving the radiation problem, direct solving the Boltzmann transport problem, and also solving the solid problem as well. That's a very basic or finite element based stuff. And also I mentioned I'm looking for collaborators, especially for this development. The first one, this is called TaiG LBM. Why is called named TaiG? Because I first introduced what is the TaiG language. This is a very it's a language basically developed by some people basically for the computer graphics community, but not for the computational mechanics. But they all support double precision and single precision. So now we use this language to writing this code, and they can run massively on multi-core CPU and GPUs. So this is published in Fluids recently, and we are capable of solving very different scale problems. We can solving the digital base, let's say, flow through a porous media, or multi-phase flow problems. This is the flow saturation and also very large scale initial dominant problem. That's like the most used in lattice Boltzmann. What is really attractive is that we only have 400 lines of code for single phase problem and 500 lines for multi-phase. So it can be very easy to use, deploy on GPUs. So yes, so it's lattice Boltzmann is very efficient, and we are focusing on algorithm development. It's we have keep the source code as minimum, and so everybody could use it or could implement their own models. It's very efficient on GPUs and parallel CPUs. But it's on shared memory only at this moment. I'm writing proposals for MPI stuff for later. And this is supporting the single phase lattice Boltzmann and multi-component lattice Boltzmann model. This is a very nice drainage process for flow into the porous media. It's a two-phase flow problems. We have benchmark with Stokes flow, Late-Drain flow, all this stuff in the GitHub repository. And recently we also add in the phase change problem for solid into changing into fluids and fluid into solids. It depends on temperature, of course, and some latent heat. And also we include a grayscale problem. This means sometimes the resolution is not very high, so we can only we have a grayscale something between 0 and 1 to simulate to like a reservoir based simulation. So in speed, in terms of speed, we're achieving very nice good speed. And in one GPU 800 GPU, we receive like 500 MLUPS, which is the number of the nodes over 1 million over computer time in seconds. So it's more or less, it compared with other very famous, let's say, Babel's code, very well maintained lattice Boltzmann code. It's equivalent to like running 5,000 cores on the using these Babel's codes. So, and also this code is maintained as very minimum, let's say 400 lines for 500 lines for multi-phase programs. It's like only 10% of what they already have in the Babel's, and everything is written explicitly. And if you're interested, I really recommend you have a look at this code. And we are now also expanding for more type of problem. We have very good benchmarks with the speed benchmark, the number of cells. This is the speed. Of course, this is not optimized. Ideally, if we run in these GPUs, we can the maximum speed will be like 2 times more, but our time implementing the code is minimum. We use a Python-like language, like named Taiji, so we don't need to touch the CUDA or don't need to touch the OpenGL stuff. That's quite impressive when I learned it. And this is the first code I'm trying to say. And the second code is about called Raven. It's a deterministic for radiation principle problems. So compare with the previous one, lattice Boltzmann is like it's not real Boltzmann. It's not real Boltzmann solver. Lattice Boltzmann we approximate the directions, and it's very basic. We have very simplified version, but here we have proper Boltzmann solver. It's aimed to solving the radiation transport problem. Let's say a photon or some lights or some neutrons. So we have a transport problem, and we have something happened and with source terms. So that is the typical things. And we're using the finite solver for this. Is that the same structure? But arbitrary as an arbitrary number of directions that we can resolve. And this is one application for the radiation transport problem. Basically, we have light source here. We shadow the UVC lights into the human, and we have ventilation problems. So we have a ventilation basically it's used for control the. This work is done 2 years ago to predict the coronavirus stuff. But this this UVC light could have directly used for shining on the people, but you can have a more. It's a very special length. It's a 222 millimeter nanometers length for the light, so that can be used directly on the people. And we have also used this solver to model a special light source there to benchmark with the already have in the lamp, and to predict the efficiencies of this nanometer 222 radiation for curing the coronavirus. And we also do, this all looks like this voxel-based simulation. So we have 2 lights there, and we have this is previously. This is the benchmark problem for this PNAS paper to benchmark the radiation efficiencies with the airflows. Consider many aerodynamics model with droplets with evaporation, but I'll skip that one. And also used for the water disinfection. It's a fully coupled radiation solver with the fluid solver as well. I'll go back to the fluid solver. So fluid solver is exactly the same. We benchmark this Navier-Stokes solver. It's all the solver I mentioned in the previous slide, but Boltzmann transport all this so finite fluid solver. It's all matrix-free based method, reducing the memory cost and running on large CPU and or GPUs. And we use that for aeronautics problem. I'll skip this slide. But we use this for digital rock physics for the permeability study of this single phase flow problems. It's a voxel-based solver. We compare this one with lattice Boltzmann and also the implicit finite volume solver, matching quite well. But the main good thing of using this one is reducing the memory cost. Even we can use similar things like lattice Boltzmann solver for this problem, but the memory cost for lattice Boltzmann is huge because it requires at least, if you have 19 directions of the lattice. So but in the finite element space, only need 3 velocity space. So that saves a lot of memory compared to the lattice Boltzmann, while achieving the same order of accuracy. So we also did this Navier-Stokes-Brakeman equations. So we have a Brakeman size in the equation. So we can model like a reservoir base. We model the relative permeabilities of this grayscale, so that we're trying to see the grayscale effect on the rocks. So that is in summary. So that's all 3 solvers I mentioned. So we have a fully coupled fluid solid radiation, and it's not really in same not really same code, but we can wrap them arbitrary as we wish. So especially for the lattice Boltzmann part, that part is open source, and looking for some more applications, for example, battery simulations or large scaled image-based simulations. And that's all I'm trying to talk about today. So any questions? Any questions?